In this video, we are going to discuss about agammaglobulinemia. Agammaglobulinemia is a rare primary immunodeficiency disorder that is characterized by very low or absent levels of immunoglobulins or antibodies in the blood. This condition arises due to failure in B cell development, which normally helps in producing antibodies to fight infections. We see the most common form of agammaglobulinemia is X-linked Agammaglobulinemia, also known as Bruton Agammaglobulinemia, named after the physician who first described it. This disorder follows an X-linked recessive inheritance pattern, which means it typically affects males and is passed down through the maternal X chromosome. The root cause of this condition is a mutation in the BTK gene, located on the X chromosome, specifically between the regions XQ21.3 and XQ22. The BTK gene plays a critical role in B cell development, and mutations in this gene disrupt that process, leading to the immunodeficiency. We see the key protein defect in this disease is the BTK here. This BTK is essential for signaling via pre-BCR. Actually, it's during the development of B cell. When we start from pro-B cell, it goes through pre-BCR signaling, and we get the B cell. And from B cell, we get the immunoglobulins or antibodies. But when BTK is absent or is defected, that time pre-BCR signaling is halted, and we do not get the conversion of pro-B cell to B cell. Thereby, we also do not get the immunoglobulins or antibodies, and that condition is the agammaglobulinemia. In this condition, there are less number of B cells and there are less number of antibodies. Now let's see the whole mechanism of this condition in a detailed manner. We see the development of B cell starts from HSC, that's hematopoietic stem cell. From here the cell differentiates into pro-B cell, where critical genetic rearrangement begins. This includes DJ joining of the heavy chain gene segments supported by IL-7 receptor signaling, which is essential for the cell survival and proliferation. Next step is the pro-B cell progresses to the pre-B cell stage, where we get the VDJ joining that completes the heavy chain rearrangement. At this point, a pre-B cell receptor or pre-BCR is expressed on the surface of cell as shown in the diagram. This pre-BCR complex is composed of successfully rearranged heavy chains paired with surrogate light chains. The pre-BCR signaling is a crucial checkpoint in B cell development, and this process is mediated by BTK or Bruton Tyrosine Kinase, which is recruited to the pre-BCR complex as shown in the animation. It must be noted here that detailed pathway of pre-BCR signaling has been discussed in separate video. Now moving further, once BTK protein is activated upon pre-BCR engagement, it initiates a signaling cascade that confirms the functionality of heavy chain and pushes the cell into next stage, that's light chain rearrangement. Following this successful rearrangement, the cell becomes an immature B cell. At this stage, it expresses a complete B cell receptor, that's BCR, on its surface, although it still resides in the bone marrow. And then we see if it passes the self-tolerance checks, meaning it does not strongly react to its self-antigens, it matures into mature B cell and exits the bone marrow to enter the peripheral lymphoid tissues. There it exists as peripheral B cell, scanning for antigens. Upon encountering a specific antigen, the B cell becomes activated and differentiates into plasma cell. Plasma cells are the antibody factories of the immune system, actively secreting antibodies which are essential for neutralizing pathogens and coordinating immune responses. Till now, all things are going normal, but we have a condition here where the BTK gene is mutated. That time we do not get the BTK protein. So BTK is unavailable and we do not get the activation of pre-BCR complex, and all further events ceases to exist. That means we do not get the B cell development, and eventually we also do not get the production of immunoglobulins. That's agammaglobulinemia. So ultimately we see when there is a mutation in BTK gene, the cell is unable to produce the BTK protein, as we already know that. But what are the consequences later on? We see without BTK protein, there is a failure in pre-BCR signaling. This causes developing B cells to undergo apoptosis. As a result, we see fewer mature B cells in circulation. And because there are fewer B cells in circulation, the production of immunoglobulins or antibodies drops significantly. This cascade of effects is what ultimately leads to agammaglobulinemia, a condition marked by severely reduced antibody levels and poor immune response. This explains the molecular basis and clinical consequences of BTK mutations in agammaglobulinemia. So this is what agammaglobulinemia is. If you found this video helpful, feel free to like, share and subscribe for more immunology insights. I hope you like the video. If you like it, give it a thumbs up. You can support my work on Patreon or YouTube and make sure to subscribe this channel. Thanks.